Welcome to 45 Minutes of Car Facts. Whether you're going to sleep or listening to this while studying, I hope you have a comfortable time listening to a comprehensive list of facts of automotive history. Let's begin. The curved Oldsmobile of 1901 was steered with a tiller, similar to a boat, rather than a steering wheel. Drivers pushed the tiller left to go right and right to go left, which felt natural to people familiar with boats, but confused everyone else. This backward steering was inherited from horse-drawn carriages where the tiller controlled which way the front axle pivoted. Steering wheels didn't become standard until several years later, when their advantages became obvious. The steering wheel allowed for finer control and required less physical space than a tiller. It also felt more intuitive to people who had never driven a boat. By 1908, tillers had almost completely disappeared from automobiles. Today, finding a tiller-steered car is extremely rare, and most are in museums. Wooden spoke wheels were standard on cars well into the 1920s. These wheels were beautiful, with typically 12 spokes radiating from a central hub like a wagon wheel. But they required constant maintenance that modern drivers would find exhausting. The wood would shrink in dry weather and swell when wet. Spokes would loosen and need tightening with a special wrench. Owners had to check spoke tension regularly to prevent wheels from collapsing. The wood also had to be protected from the elements. Varnish or paint helped, but the constant exposure to road spray, mud, and weather took a toll. Wire wheels replaced wooden wheels in the 1920s, using tension steel spokes that didn't require the constant maintenance of wood. Stamped steel wheels became common by the 1930s, finally ending the need for regular wheel maintenance altogether. The progression from wood to wire to steel happened surprisingly quickly once the alternatives became available. The brass era of automobiles, from roughly 1896 to 1915, got its name from the extensive brass fittings on cars of that period. Headlamps, side lamps, horn, radiator, and various trim pieces were made of brass. This wasn't purely decorative. Brass was relatively easy to work with, didn't rust like iron, and could be cast into complex shapes. It was a practical choice given the manufacturing technology of the time. However, brass tarnished quickly, turning from shiny gold to dull brown or green if not maintained. Owners spent considerable time polishing all this brass to keep their cars looking presentable. Special brass polish and soft cloths were essential supplies for any car owner. Polishing the brass on a large car could take hours. Some wealthy owners had servants whose job included keeping the car's brass polished. When nickel plating became affordable in the mid-1910s, it quickly replaced brass because it didn't tarnish. A nickel-plated fitting would stay shiny with minimal care. The transition from brass to nickel marked the end of the brass era and the beginning of a more modern aesthetic in automobiles. Today, brass-era cars are prized by collectors partly because of those beautiful brass fittings that require so much care. Chain drive was common on early cars, with the engine turning a chain that connected to the rear axle. Similar to a bicycle, the chain ran from a sprocket on the transmission to sprockets on each rear wheel. This was simple and easy to understand, which made it popular with early manufacturers who were still figuring out how to build automobiles. But chain drive had significant drawbacks. The chains were noisy, clanking and rattling as they turned. They required constant lubrication to prevent wear. Even with proper maintenance, chains stretched and wore out relatively quickly. Exposed chains could also be dangerous, catching clothing or fingers if you got too close. Some manufacturers enclosed the chains in metal covers, but this made maintenance more difficult. Shaft drive, using a drive shaft and differential, proved more reliable and became universal by 1920. The drive shaft was enclosed, quieter, required less maintenance, and lasted much longer than chains. The differential allowed the rear wheels to turn at different speeds when cornering, which chains couldn't easily accommodate. A few specialty vehicles used chain drive into the 1930s, but for mainstream automobiles, shaft drive was clearly superior. Detachable cylinder heads weren't common until the 1920s. Earlier engines had heads cast as part of the engine block in one piece. This made the engine simpler to manufacture initially, but it created enormous maintenance problems. If you needed to service the valves, replace a head gasket, or do any work inside the combustion chambers, you had to remove the entire engine from the car. This process could take days. The engine had to be disconnected from the transmission, all the cooling system hoses removed, the exhaust disconnected, and the engine physically lifted out of the car. Only then could you access the valves and combustion chambers. After completing the work, you had to reinstall the entire engine and reconnect everything. What should have been a simple maintenance job became a major undertaking. Detachable heads made maintenance much simpler. You could remove just the cylinder head, leaving the engine in the car. This turned a multi-day job into something that could be done in hours. But some manufacturers resisted the change for years, claiming one-piece construction was stronger and less likely to develop leaks. Eventually, the maintenance advantages of detachable heads won out, and by the late 1920s, they were nearly universal. Coach builders were companies that built custom bodies for car chassis. In the early decades of automobiles, many manufacturers sold just a chassis with engine and running gear. This wasn't a complete car, just the mechanical components. Wealthy customers would then commission a coach builder to create a custom body to their specifications. It was similar to buying a custom suit rather than one off the rack. The process could take months. The customer would meet with the coach builder to discuss exactly what they wanted: how many doors, what style of roof, what material for the interior. The coach builder would create drawings for approval. Once approved, craftsmen would build a body entirely by hand. Wood frames were shaped and assembled. Metal panels were formed and fitted. Interior trim was custom-made. Each body was unique, hand-built to the customer's requirements. No two were exactly alike. Even if two customers ordered similar designs, small differences in dimensions, materials, or details made each one individual. This meant that repair work was complicated. If you damaged a custom body, you couldn't just order replacement parts. Everything had to be custom-made again. The practice continued into the 1940s for the most expensive cars, though it became less common as manufacturers began offering more body styles. By the 1950s, full custom coach building was essentially dead for new cars, replaced by limited customization options from a manufacturer. Today, a handful of ultra-luxury manufacturers still offer limited coach-built bodies, but the golden age of coach building ended decades ago. Figoni E.T. Falaschi was a French coach-building firm famous for their aerodynamic designs in the 1930s. Giuseppe Figoni and Ovidio Falaschi created some of the most stunning automobiles ever built. Their bodies featured flowing curves that seemed to defy the limitations of metal. Covered rear wheels, teardrop shapes, and smooth surfaces characterized their work. They were years ahead of mainstream design. Their designs weren't just beautiful. They were actually aerodynamic at a time when most car designers didn't think about wind resistance. The flowing shapes and covered wheels reduced drag, improving top speed and fuel economy. Of course, these benefits were secondary to the stunning appearance. Figoni E.T. Falaschi bodies were rolling art, sculptures that happened to be functional vehicles. The bodies were typically built on high-performance French chassis like Delahaye, Talbot Lego, and Bugatti. A Figoni E.T. Falaschi body could cost as much as a chassis itself, doubling the price of an already expensive car. Only the wealthy could afford them. Production numbers were tiny, often just one or two examples of each design. Today, they're among the most valuable pre-war automobiles, selling for millions of dollars when they rarely come to market. The Brewster Coach Building Company in America built bodies for the wealthiest families. Brewster had been building horse-drawn carriages since 1810 and transitioned to automobile bodies in the early 1900s. They brought nearly a century of woodworking and metalworking expertise to automobile coach building. Their reputation for quality was impeccable. Brewster Town cars feature luxurious interiors with fine leather upholstery, exotic wood trim, and even silver or crystal flower vases. Some had glass partitions separating the chauffeur from passengers, with speaking tubes for communication. The chauffeur's compartment might be open or have a removable top, while passengers enjoyed a fully enclosed cabin. Heat and weather protection were for the passengers. The chauffeur was expected to endure the elements. Brewster bodies were known for conservative, elegant styling that emphasized quality over flash. They didn't follow fashion trends but maintained a timeless, dignified appearance. Brewster clients wanted their cars to project wealth and good taste without being ostentatious. The conservative styling meant Brewster body cars looked elegant for decades rather than becoming quickly dated. Brewster tried building complete cars under their own name in the 1920s, but couldn't compete with mass-produced vehicles. They returned to coach building but never regained their earlier prominence. The company closed in 1937, a victim of the Depression and changing market conditions. Today, Brewster body cars are prized by collectors for their exceptional quality and elegant styling. Shooting brakes were originally custom wagon bodies built on luxury car chassis for British aristocrats going hunting. The term shooting refers to hunting game birds. Brake was an old term for a wagon, so a shooting brake was literally a hunting wagon. The rear cargo area was designed to carry guns, hunting dogs, and dead game. These weren't crude utility vehicles. They were custom built on expensive chassis like Rolls-Royce or Bentley. The front seats offered luxury car comfort for the lord and his gamekeeper. The rear cargo area had custom fittings for securing guns and provisions. Often there were folding seats for additional passengers or beaters. Everything was designed to be both functional and befitting the owner's status. After World War II, some manufacturers offered shooting brake models as part of their regular lineup, though they were usually called estate cars or station wagons. Aston Martin, Bristol, and other British luxury makers built small numbers of shooting brakes through the 1960s. Today, the term describes any luxury wagon or estate car, though few modern buyers use them for hunting. The shooting brake has become a style rather than a function. Modern recreations occasionally appear, with coach builders converting luxury cars into wagons. But true shooting brakes are rare. The cost of custom coach work make them impractical except as marketing exercises or one-off projects for very wealthy individuals. The golden age of the shooting brake ended when station wagons became common and lost their association with wealthy sportsmen. Convertible tops were canvas stretched over a folding frame. Early tops were difficult to raise and lower, requiring multiple latches and considerable effort. You had to unlatch the top from the windshield frame, then manually push it back while trying to guide the folding frame mechanism. Getting it to fold properly required practice. Once folded, you had to secure it with straps or a cover to prevent it from flapping in the wind. These canvas tops leaked almost from new. Water would seep through the fabric, drip at seams, and pull in any slight depression in the material. After a few years, the canvas would become brittle and crack. Replacement tops were expensive and required skilled installation. In cold weather, the canvas would stiffen, making it even harder to raise or lower. The plastic rear windows would crack and turn yellow. Power tops appeared in the 1940s, making convertibles more practical. Electric or hydraulic motors did the heavy lifting, and latches became automatic. The driver just pressed a button and waited while the top raised or lowered itself. This made convertibles accessible to anyone, not just those with the strength and patience to wrestle with a manual top. Modern fabric tops are waterproof and insulated, solving most of the traditional convertible problems. Multiple layers of fabric, sound-deadening material, and proper seals make modern convertible tops nearly as quiet and weatherproof as fixed roofs. They last much longer than old canvas tops. Glass rear windows are standard. Some tops can even be lowered while driving at highway speeds. The convertible has evolved from a fair-weather vehicle into something practical year-round. Speedometers became common in the 1910s, but early versions were notoriously inaccurate. They used mechanical cables connected to the transmission or wheel. A flexible cable, similar to a modern speedometer cable, spun at a rate proportional to vehicle speed. This turned a magnet inside the speedometer, which dragged a needle against a spring. The faster the magnet spun, the farther it pulled the needle. Any slippage in the cable or wear in the gears would throw off the reading. Temperature changes affected the cable flexibility. If the cable kinked or got pinched during installation, it might not spin freely. Some speedometers were optimistic, reading higher than actual speed. This made cars seem faster than they were. Others were pessimistic, reading low. This could get you a speeding ticket, even when your speedometer showed you were within the limit. Drivers learned not to trust them completely. Experienced drivers would judge speed by engine sound, feel, and how fast landmarks passed. The speedometer was a rough guide at best. Calibration required special equipment and was rarely done. Even new speedometers could be off by 10% or more. This inaccuracy was just accepted as part of driving. Modern electronic speedometers are much more accurate, using wheel speed sensors or GPS data. They're typically within 1 or 2% of actual speed. Some are deliberately optimistic by a small amount to reduce the chance of speeding tickets. But even modern speedometers aren't perfect. Tire size changes from wear or replacement can affect accuracy, but they're far better than the mechanical speedometers they replaced. Oil pressure gauges were critical on early engines that had primitive lubrication systems. These engines used splash lubrication, where moving parts simply splashed oil around inside the crankcase. This wasn't very efficient, and oil pressure could drop dangerously low if oil level fell or the engine ran too hot. Without adequate oil pressure, bearings would fail in minutes or even seconds. Drivers had to watch the gauge constantly, particularly on long trips or in hot weather. A drop in oil pressure meant you needed to stop immediately and find out why. Maybe the oil level was low and just needed topping up. Maybe the engine was overheating and needed to cool down. Or maybe something had failed and the engine was about to destroy itself. The oil pressure gauge was your early warning system. Modern warning lights have replaced gauges in many cars, but enthusiasts still prefer gauges that show actual pressure rather than just a warning when pressure is already dangerously low. A gauge lets you see trends. If pressure gradually decreases over time, you know something is wearing out and needs attention soon. A warning light only tells you when the problem has already become serious. By then, damage may have already occurred. Some modern cars use dummy gauges that look like real gauges but actually just show normal or warning, with no real measurement in between. These fool owners into thinking they have real gauges while providing no more information than a warning light. Enthusiasts consider this deceptive, a cost-cutting measure disguised as proper instrumentation. Voltmeters show the electrical system voltage, indicating whether the generator or alternator is charging the battery properly. A healthy charging system should show around 14 volts when the engine is running. If the voltmeter shows 12 volts or less with the engine running, the charging system isn't working. The battery is powering everything, and it will go dead soon. 13.5 to 14.5 volts indicates proper charging. Many modern cars replace the voltmeter with a simple battery icon that illuminates if there's a problem. This is cheaper to manufacture and simpler for non-technical owners, but it provides no early warning. The warning light only comes on when the problem is already serious. A voltmeter shows gradual changes in charging voltage that indicate a problem is developing before complete failure occurs. Watching a voltmeter can also help diagnose electrical problems. If voltage drops when you turn on certain accessories, you know those accessories are drawing excessive current. If voltage is higher than normal, the voltage regulator might be failing, which can damage the battery and electrical components. A voltmeter provides useful information that a simple warning light cannot. Manifold vacuum gauges were popular in the 1970s and 1980s as fuel economy aids. Manifold vacuum is a suction created in the intake manifold when the throttle is mostly closed. Higher vacuum readings indicate efficient engine operation and light throttle. Lower vacuum meant you were accelerating hard or climbing a hill using more fuel. Drivers could use the gauge to modify their driving style for better economy. The gauge taught drivers to accelerate gently and maintain steady speeds. Watching the vacuum needle, you could learn to use the minimum throttle needed for any situation. This made a real difference in fuel economy, sometimes improving it by 10 or 20%. Skilled drivers could extract impressive mileage from cars that weren't particularly efficient by driving in a way that kept vacuum high. As fuel injection replaced carburetors and engines became more efficient, vacuum gauges disappeared from most vehicles. Modern engines with electronic throttle control and variable valve timing don't have the same direct relationship between manifold vacuum and fuel consumption. Fuel economy displays now show instant and average fuel consumption in miles per gallon or liters per 100 kilometers, providing similar information in a more direct way. Inclinometers show the angle of tilt, useful for off-road vehicles to indicate how steep a slope you're climbing or how much the vehicle is leaning in a side slope. Early inclinometers were simple devices with a ball bearing rolling along a curved scale or a bubble level in fluid. They showed tilt angle but weren't very precise. They didn't require power and couldn't fail electrically, but they were hard to read accurately, especially in a bouncing vehicle. Some luxury SUVs include digital inclinometers as part of their off-road information systems. These use electronic sensors to measure pitch and roll angles precisely. The display might show both front-to-back tilt and side-to-side lean simultaneously. Some systems include a compass and altitude reading, creating a comprehensive off-road information display. The graphics can be quite elaborate, showing a three-dimensional representation of the vehicle's orientation. Most owners never use them for their intended purpose. The inclinometer becomes just another interesting display to scroll through, occasionally amusing passengers, but rarely providing information that affects driving decisions. In serious off-road situations, experienced drivers judge angles by feel and visual reference rather than by looking at a gauge. But the inclinometer does provide bragging rights and looks impressive on the specification sheet. Studebaker began as a wagon manufacturer in 1852, building covered wagons for pioneers heading west across America. Brothers Henry and Clement Studebaker started making wheelbarrows and wagons in South Bend, Indiana. During the Civil War, they supplied wagons to the Union Army, which established their reputation for quality. After the war, Studebaker became one of America's largest wagon manufacturers. They built their first automobile in 1902, initially as a diversification move, while continuing to build wagons. As automobiles became more popular, Studebaker gradually shifted focus from wagons to cars. By 1920, they had stopped building wagons entirely, devoting all their production to automobiles. The transition from wagon maker to automobile manufacturer was remarkably successful for several decades. Studebaker became a significant manufacturer, building innovative and often stylish cars. They merged with Packard in 1954 in an attempt to create a stronger competitor to the big three automakers. However, neither brand survived. Packard production ended in 1958, and the last Studebaker was built in Canada in 1966. The company that had survived the transition from wagons to automobiles couldn't survive the competitive pressure from larger manufacturers. Their distinctive designs, particularly the bullet-nosed models of 1950 to 1951, remain memorable. The bullet nose featured a chrome spinner in the center of the grille that looked like an aircraft propeller or bullet. It was either loved or hated, with no middle ground. Studebaker also built the beautiful Raymond Loewy design coupes of 1953 to 1964, which are still admired today. Despite some excellent designs, Studebaker couldn't achieve the sales volume needed to survive. Nash Motors introduced several innovations, including the first mass-produced car with seat belts as standard equipment in 1949. This was years before seat belts became common, let alone mandatory. Nash also offered a reclining front seat that converted into a bed, marketed as the Nash Airflight bed. This made the car appealing for travelers who wanted to sleep in their car rather than pay for a hotel. Nash introduced the first American compact car, the Rambler, in 1950. At a time when American cars were getting bigger and more powerful, the Rambler offered efficiency and practicality. Initially, it wasn't very successful, but when the economy turned down in the late 1950s, compact cars suddenly became attractive. Rambler sales soared, making it one of America's best-selling brands for a few years. Nash merged with Hudson to form American Motors Corporation in 1954. The Nash name disappeared from new cars after 1957, though the Rambler continued under the AMC banner. AMC survived as an independent manufacturer until being absorbed by Chrysler in 1987. Nash's legacy lived on to the Rambler name, and AMC's focus on smaller, more efficient vehicles. Hudson was known for step-down design in the late 1940s and early 1950s. Instead of sitting on top of the frame rails like most cars, the passenger compartment floor was lower than the frame. You literally stepped down into the car. This allowed lower overall height while maintaining headroom. It also lowered the center of gravity, improving handling significantly. This handling advantage was immediately apparent. Hudson Hornets dominated NASCAR in the early 1950s because of this handling advantage combined with powerful six-cylinder engine. From 1951 to 1954, Hudson's won more NASCAR races than any other manufacturer. The step-down design made them nearly unbeatable on the stock car circuit of the era. The step-down design was beautiful but expensive to build. The complex body structure required more labor than conventional designs. Hudson was a smaller manufacturer that couldn't afford the tooling cost to update the design frequently. By the mid-1950s, the step-down design was aging, and Hudson lacked the money to replace it. The merger with Nash formed AMC, but Hudson as a separate brand ended after 1957. Kaiser Frazer was an ambitious attempt to create a new American car company after World War II. Henry Kaiser, who had made a fortune building Liberty ships during the war, partnered with Joseph Frazer, an experienced automotive executive, to build cars. They purchased a massive government-built factory in Willow Run, Michigan, that had built B-24 bombers during the war. Kaiser Frazer achieved some success in the late 1940s when new cars were in short supply and demand was enormous. Their cars were unconventional, with front-wheel drive on some models years before it became common. They offered interesting features and styling. But as the Big Three ramped up production, Kaiser Frazer couldn't compete. Their production volumes were too low to achieve the economies of scale needed to match Big Three pricing. The company struggled through the early 1950s, building cars that were well-designed but expensive compared to Ford, Chevrolet, or Plymouth. The last Kaiser was built in 1955. The company continued building Jeeps, which they had acquired from Willis, for a few more years before selling the Jeep operation to AMC in 1970. Kaiser Frazer proved that building cars successfully required scale that new entrants couldn't achieve. DeSoto was Chrysler's mid-price brand, positioned between Plymouth and Dodge. Introduced in 1928, DeSoto was meant to capture buyers who wanted something better than Plymouth but couldn't afford a Chrysler. The strategy worked well for 3 decades. DeSoto sold well, offering distinctive styling and features that justified its price premium over Plymouth. By the late 1950s, the market for mid-price brands was shrinking. Buyers were either choosing economy cars or luxury cars, with less interest in the middle ground. All the mid-price brands suffered. Chrysler discontinued DeSoto in 1961 after selling over 2 million cars over 33 years. The 1961 models were essentially rebadged Chryslers, the result of cost-cutting as the brand wound down. Today, DeSotos are popular with collectors for their distinctive styling, particularly the models from the mid-1950s with their bold chrome grills and tail fins. The 1955 to 1956 DeSoto Fireflight is particularly sought after, with powerful V8 engines and stunning styling. The Adventurer model of 1956 was one of the fastest cars of its era. Though the brand is gone, DeSoto left behind some memorable automobiles. Disc brakes were developed for racing before appearing on road cars. The basic principle had been known for decades, but making it work reliably took time. Racing provided the incentive to solve the problems because the improved braking could mean the difference between winning and losing. Early disc brakes were temperamental, sensitive to heat, and required exotic materials. The Chrysler Imperial offered them in 1949, the first American production car with disc brakes. But the early design was problematic. The brakes worked well when cold, but faded badly when hot. The calipers would leak. Pad wear was excessive. Within a year, Chrysler discontinued them and went back to drum brakes. The technology wasn't ready for production use yet. British sports car makers adopted disc brakes in the 1950s with better results. Jaguar used disc brakes on their C-Type race cars with great success, then offered them on road-going XK models. The development work in racing had solved many of the earlier problems. By the 1960s, front disc brakes became common on performance cars, providing much better stopping power than drums. Rear disc brakes followed later as the technology matured. Today, disc brakes are universal on the front of every car and on all 4 wheels of most cars. They're more effective, provide better modulation, dissipate heat better, and are easier to service than drum brakes. Racing development proved the concept and worked out the problems before mass production adoption. It's a classic example of racing technology eventually benefiting everyday drivers. Ground effects in racing use the vehicle's underbody shape to create low pressure underneath, sucking the car toward the track. This provides downforce without the drag penalty of large wings. The concept revolutionized racing car design in the late 1970s. Lotus pioneered ground effects in Formula One, and their cars dominated for several seasons until other teams copied the technology. Ground effects cars had side pods shaped like inverted airfoils, with sealed skirts that touch the ground to maintain the low pressure underneath. As air flowed under these shaped tunnels, it accelerated, creating suction by the Bernoulli principle. The faster the car went, the more downforce it generated. This allowed cars to corner at incredible speeds. The technology worked too well. Cars became dangerously fast. If the skirts were damaged or lifted from the ground, the downforce disappeared instantly, often causing crashes. Formula One banned ground effects for safety reasons in 1983. However, the basic principles continue in modern race cars, which use carefully shaped underbodies to generate downforce without the extreme ground effect tunnels and skirts. Road cars occasionally incorporate ground effects principles on a much smaller scale. Ferrari, Porsche, and other sports car manufacturers use underbody aerodynamics to increase downforce. The effects are modest compared to race cars, but still improve high-speed stability. As computational fluid dynamics has improved, designing effective underbody aerodynamics has become easier, and more road cars benefit from these principles. Slick tires, with no tread pattern whatsoever, provide maximum grip on dry pavement. All the rubber contacts the road rather than having grooves that reduce contact area. The soft rubber compounds used in racing slicks become sticky when heated to operating temperature, creating enormous grip. Slicks are illegal for street use, but universal in dry weather racing. In wet conditions, slicks are dangerous because they can't evacuate water and hydroplane easily. The development of tire compounds that work best at specific temperatures has become a critical part of racing strategy. Some compounds work best at lower temperatures, providing grip immediately but degrading quickly. Other compounds need higher temperatures to work but last longer. Choosing the right compound for the conditions and race length is crucial for success. Modern racing slicks are incredibly sophisticated. The rubber is formulated differently for different parts of the tire. The shoulder compound might be harder than the center to resist the extreme forces in corners. Temperature sensors inside the tires provide real-time data. Tire pressure must be set precisely because it affects both grip and wear. The simple-looking slick is actually a highly engineered component. Street performance tires incorporate some racing tire technology. Soft compound street tires in maximum performance categories provide impressive grip, though nothing like racing slicks. Some street-legal track tires are nearly slicks, with minimal tread depth just sufficient to meet legal requirements. These provide some of the performance of true slicks while being street legal, though they wear quickly and are expensive. Telemetry systems allow racing teams to monitor hundreds of data points in real time as the car races. Engineers can see tire temperatures, brake temperatures, engine parameters, suspension movement, fuel consumption, and countless other measurements. This data streams wirelessly from the car to the pit, where engineers analyze it and communicate advice to the driver. The amount of data is staggering. Modern Formula One cars transmit gigabytes of data during each race. Every sensor is monitored continuously. Engineers can spot problems before they become failures. They can verify that the car is performing as expected. They can optimize strategy based on how the car is behaving. The driver may report that the car feels strange, and telemetry can show exactly what's wrong. Telemetry has changed racing strategy. Teams can monitor tire wear and performance, choosing pit stop timing to optimize advantage. Fuel consumption can be tracked precisely, allowing fuel savings when possible and full performance when needed. Brake temperatures might indicate that brake cooling ducts need adjustment. Every aspect of car performance can be optimized based on real data rather than guesswork. Some series restrict telemetry to keep costs down and increase driver importance. NASCAR limits telemetry, forcing teams to rely more on driver feedback. This keeps the racing closer and makes driver skill more important. But unrestricted series use every bit of telemetry available, pushing the technology constantly forward. Roll cages protect drivers in racing accidents by creating a strong structure around the driver. Early roll bars were simple hoops behind the driver's seat. They provided some protection if the car rolled over, but didn't protect against side impacts or frontal impacts. As racing speeds increased and crashes became more violent, simple roll bars proved inadequate. Modern roll cages are complex structures with tubes carefully placed to protect against impacts from any direction. The main hoop behind the driver connects the front bars extending toward the firewall, side bars protecting the doors, rear bars supporting the main hoop, and crossbars distributing impact loads. All these tubes must be precisely positioned and welded to create an integrated protective structure. Racing regulations specify roll cage construction in detail. Tube diameter, wall thickness, material, bending method, welding procedures. Everything is regulated to ensure adequate strength. Cages must be built by certified fabricators who understand both the regulations and the engineering principles. A poorly built cage might pass visual inspection but fail in a crash with potentially fatal results. Some street performance cars have roll cages for track use. However, roll cages in street cars create issues. The bars are hard and unforgiving. In a street accident, you might hit your head on the cage. Padding helps but isn't fully effective. Roll cages belong in dedicated race cars with drivers wearing helmets and proper restraints, not in street-driven vehicles. Wind tunnels allow engineers to study how air flows around vehicles without building full-size prototypes or testing on the road. Early automotive wind tunnels were crude affairs, often adapted from airplane wind tunnels. They couldn't accurately replicate real-world conditions. The car sat stationary while air blew over it, but this didn't perfectly simulate a car moving through still air. The boundary layer on the tunnel floor affected results. Modern facilities can simulate different speeds, crosswinds, and even rain. The most advanced tunnels have rolling road floors that move at the same speed as the simulated wind. This allows realistic testing of how air flows under the vehicle, which is critical for modern aerodynamic development. Some tunnels can vary temperature and altitude to simulate different conditions. Cars are tested at multiple wind angles to understand how they behave in crosswinds. Wind tunnel testing is expensive. Each hour of testing can cost thousands of dollars, but it's still cheaper than building multiple prototype vehicles and testing them on the road. Wind tunnels also allow testing in controlled, repeatable conditions. Road testing is affected by weather, traffic, and countless other variables. In the wind tunnel, you can isolate specific effects and understand exactly how changes affect performance. Computational fluid dynamics has supplemented wind tunnel testing in recent years. Computers can simulate airflow and predict how design changes will affect aerodynamics. This allows engineers to evaluate hundreds of variations before building anything physical. However, CFD isn't perfect. Wind tunnel testing remains essential to verify that computer predictions match reality and to catch unexpected effects that simulations might miss. Water channels use flowing water with dye to visualize airflow patterns. Water flows much slower than air but behaves similarly according to fluid dynamics principles. Engineers inject colored dye into the water flow and watch how it moves around scale models of vehicles. The dye makes flow patterns visible in ways that airflow cannot be seen. Engineers can see exactly where air separates from the vehicle surface, creating turbulent flow and drag. They can watch vortices form and understand where energy is being wasted. The visual nature of water channel testing makes it invaluable for understanding complex flow patterns. Many improvements in aerodynamics started with observations in water channels that suggested design changes, later verified in wind tunnels. Water channel testing uses scale models rather than full-size vehicles. The models must be precisely manufactured to match the proposed design. Even small imperfections can affect flow patterns, so models are often machined from solid blocks of material or 3D printed with great precision. Multiple models might be tested to evaluate different design variations. The beautiful thing about water channels is that you can literally see the problem and the solution. Acoustic wind tunnels measure wind noise, as well as aerodynamic forces. Microphones positioned throughout the tunnel pinpoint exactly where noise is generated. Is it the mirrors, the door seals, the windshield wipers, the A-pillar where the windshield meets the roof? Acoustic testing identifies the sources so engineers can focus on the biggest noise contributors. Engineers can then modify mirror shapes, adjust door seal designs, change wiper designs, or alter body contours to reduce wind noise. Modern luxury cars are remarkably quiet at highway speeds thanks to acoustic testing. The reduction in noise isn't just for comfort. Lower noise levels reduce driver fatigue on long trips, making cars safer. What seems like a luxury feature actually has real safety benefits. Some acoustic tunnels use arrays of microphones and sophisticated software to create visual maps showing exactly where noise originates. These maps reveal problem areas that might not be obvious. A small gap or sharp edge that creates noise far out of proportion to its size can be identified and corrected. The level of detail in modern acoustic testing is remarkable. Climatic chambers expose vehicles to extreme temperatures, from far below zero to over 120 degrees Fahrenheit. Cars are started, driven on dynamometers, and tested in these conditions to ensure everything works properly. Does the engine start reliably in extreme cold? Do the door seals remain flexible? Does the air conditioning keep the cabin comfortable in extreme heat? Engineers test materials to verify they don't become brittle in cold or melt in heat. Electronics must function across the entire temperature range. Fluids must flow properly. Batteries must provide adequate power for starting. Even things like the fit of panels are checked as materials expand and contract with temperature changes. A car designed to sell globally must work in Alaska and Arizona, Norway and Nevada. Desert testing in places like Death Valley complements climatic chamber work, providing real-world validation of engineering. The intense heat and bright sunlight of the desert test cooling systems, air conditioning, materials, and paint. Engineers drive cars for thousands of miles in these brutal conditions, looking for any problems that only appear with sustained exposure to extreme heat. What works in a climatic chamber for a few hours might fail in the desert after days of use. Cold weather testing in places like northern Alaska or Sweden tests starting, heating, and cold weather drivability. Extremely cold temperatures reveal problems that wouldn't appear in moderate climates. Does the transmission shift smoothly when the fluid is thick from cold? Do the brakes work before they warm up? Can you see clearly when snow and ice accumulate? Does the defroster work effectively? These real-world tests catch problems that laboratory testing might miss. Rough road testing facilities have surfaces with bumps, potholes, and various imperfections to test suspension durability and interior rattle resistance. Cars drive over these surfaces repeatedly, while engineers listen for squeaks and rattles. Accelerometers measure vibrations. Cameras record how panels and components move. The goal is to identify and eliminate any source of unwanted noise or vibration. Modern cars are remarkably rattle-free compared to cars from decades ago. This is the result of improved materials, better assembly techniques, and extensive testing. Engineers now understand how to isolate components, use proper fasteners, and design parts that don't buzz or rattle even after years of use. The quiet, solid feel of a modern car is no accident. It's the result of countless hours of testing and refinement. Some facilities have surfaces that simulate specific roads known to cause problems. If there's a particular rough road or bridge expansion joint that generates complaints, engineers can measure its characteristics and recreate it at the test facility. This allows them to reproduce the problem in a controlled environment, develop a solution, and verify the fix without repeatedly driving to the problem location. Durability testing drives cars over rough surfaces for hundreds of thousands of miles, equivalent to years of normal use compressed into months. Components are pushed to failure to identify weak points. Suspensions are cycled millions of times. The goal is to ensure that the car will hold up through years of normal use. If something is going to fail at 80,000 miles, better to discover that during development and fix it than have customers experience failures. The automobile has evolved in countless ways since those early days of tiller steering, wooden wheels, and brass fittings. Each generation has brought improvements, innovations, and occasionally ideas that didn't work quite as planned. But through it all, the essential character of the automobile has remained constant, a machine that provides freedom, independence, and the ability to travel wherever roads lead. These facts, these small details of automotive history and engineering, represent the accumulated knowledge of millions of engineers, designers, mechanics, and drivers over more than a century. Each innovation solved a problem, improved safety, made driving more pleasant, or simply made cars more interesting. The progression from primitive machines to sophisticated modern vehicles has been gradual, built on countless small improvements. As you drift towards sleep, perhaps you're thinking of a favorite car from your past, a memorable road trip, or simply appreciating the technological marvels that we often take for granted. These machines that carry us safely day after day are the result of all this accumulated knowledge and refinement. Every time you turn a key or press a start button, you're benefiting from over a century of continuous improvement. Rest peacefully now. Let these thoughts fade as sleep approaches. Feel your breathing slow even further. Notice how heavy your body feels, sinking into the mattress. Your mind is quiet. Your muscles are relaxed. Tomorrow is far away. For now, there is only rest. Sleep deeply. Dream pleasantly. And may your journeys, both in dreams and in waking life, always be smooth and peaceful. Good night.